In this video, we're going to review the fundamental theorem of calculus, at least one of the parts. All right, so one of our major topics that we've learned about is integrals. Integrals represent the area under a curve, and the denotation is, the elongated s, the integral symbol. Our bounds a to b tell us where our area starts and ends, and our function. All right, and then we learned that we could approximate these areas using Riemann sums, so we'll review that again at a later date. Then we could find them geometrically. But for most integrals, we're going to use the fundamental theorem of calculus. And the fundamental theorem says if I want to find this exact area, I take an antiderivative, so I undo the derivative process. I plug in the top bound. I subtract when I plug in the bottom bound. All right, and really our only tool we had when we first learned the fundamental theorem of calculus is the reverse power rule. And that's just the opposite of the derivative power rule. We add 1 to the exponent and divide by the new exponent. And I forgot the plus c. All right, so in this example, I forgot an x. I look at this example and it looks pretty straightforward. You could take integral of x and x squared plus 3x, but you can't take the integral of multiplication, so I actually have to simplify first. And write this as x cubed plus 3x squared dx. Now I have something that's just powers of x. I can do the antiderivative. X cubed becomes x to the 4th over 4. 3x squared becomes 3x cubed over 3. And I'm going to evaluate that from 1 to 2. Before I evaluate, I'm just going to write it a bit simpler because that last term is just x cubed. And now the big thing is you plug in that top bound first. So I'm going to plug in 2 first. And I'm going to subtract when I plug in the bottom bound, 1. Now I just simplify the kind of parentheses separate from each other. So 2 to the 4th, 2, 4, 8, 16. 16 divided by 4 is 4. 2, 4, 8. And that's 12. So my first parentheses is 12. 1/4 plus 1 is 5/4. All right. And a lot of times for multiple choice questions, they won't actually make you combine the fractions at the end, but we can. This is 48 over 4 minus 5 over 4 is 43 over 4. And that would be our final answer for this problem. Another one looks complicated. You can't undo the quotient rule. So we need to figure out another thing we can do. One of the other techniques we learned is that you can split up a fraction into 2 fractions. You can really only do this when there's just a single term on the bottom. 1 plus x to the negative 2. But now that I rewrite it as a simpler thing, no fractions and just powers of x, I can do my antiderivative. X plus x to the negative 1 over negative 1, evaluated from 0 to 1. Again, just rewriting it a little bit simpler. All right, the negative is going to go there. X to the negative 1 is 1 over x. And then I plug in the top bound. And it's not possible because 1 over 0 is infinity. So this one just does not exist. I did not mean for that to happen, and that wouldn't happen on the AP test, right? But just to show, just making up problems out of nowhere, it doesn't always work out. All right, here's one for you to try on your own. This one will work out because it's a nicer problem. All right, but find this integral using our fundamental theorem of calculus. I'll show you the answer in 3, 2, 1. And the answer I got was 14. This one you can just directly take the antiderivatives, plug in your values, and simplify. All right, so a quick summary. To find an integral using the fundamental theorem of calculus, you take the antiderivative first, and then plug in the bounds. I always look to simplify your problem first before you do anything more complex like we'll learn in the future, because you can see for all these ones we can do just using the reverse power rule and nothing more complicated, even though the original problems might have looked a little bit more difficult.